All right, let's dive into one of the most essential chapters in Class 11 physics, the thermal properties of matter. We're going to break down everything you need to know about how heat and temperature really shape our world, from the tiniest particles all the way up to massive weather systems.
Have you ever wondered about this? It's a classic physics puzzle. And by the end of our session today, you won't just know the answer, you'll get the deep principles behind it. We're going to tackle this puzzle and a whole lot more as we explore just how much heat affects everything around us.
So here's our game plan. We'll kick things off by getting the basics straight: heat and temperature. Then we'll see how stuff expands when it gets hot. After that, we'll get into how heat can actually change the state of matter, how heat moves around, and then we'll wrap it all up with a review of the key formulas you've got to know.
First things first, let's lock down the two most fundamental ideas here: heat and temperature. Now, you hear people use these words like they're the same thing all the time, right? But in physics, they are totally different. And honestly, getting this distinction right is the key to understanding everything else that follows.
So here's the bottom line. Temperature is all about the internal energy of something. Think of it as a measure of how fast its molecules are jiggling around. Heat, on the other hand, well, that's the energy that's on the move, from a hotter thing to a colder thing. So temperature is a property, but heat is energy in transit. Big difference.
Now, to actually measure temperature, we use a few different scales, and you gotta know how to switch between them. Here are the formulas for Celsius, Fahrenheit, and Kelvin. And remember, the Kelvin scale is a big deal in physics. It's called the absolute scale because its 0.0 Kelvin is absolute zero. That's the theoretical point where all molecular motion just stops. A nice little tip: the conversion between Celsius and Kelvin is super easy because the size of 1 degree is exactly the same.
Next up, the ideal gas law. This is a foundational equation. You'll see it everywhere. What it does is amazing. It connects the big macroscopic properties of a gas, like its pressure and volume, directly to its absolute temperature. It shows us that for a gas, temperature isn't just some number, it's directly tied to its physical state.
Okay, now that we've got a handle on temperature, let's see what happens when we change it. So, what happens when you add heat energy to something? Well, those molecules start jiggling faster, they push each other further apart, and voila, the object gets bigger. We call this phenomenon thermal expansion.
This picture illustrates it perfectly. There are basically three ways matter can expand. A long, thin object, like a rod, gets longer. We call that linear expansion. A flat sheet expands in 2 dimensions. That's area expansion. And a 3D object, like this cube, expands in all 3 dimensions, volume expansion. See? It's the same basic principle, just playing out in 1, 2, or 3 dimensions. So how do we actually calculate this expansion? We use this formula for linear expansion. It tells us that the fractional change in length, how much it grew compared to its original size, is directly proportional to the change in temperature. That little symbol, alpha, is the coefficient of linear expansion. It's basically a number that's unique to each material. Copper, for example, has a higher alpha than steel, so it expands more when you heat it by the same amount.
Now here's a really cool and useful trick. We can easily connect volume expansion to linear expansion. Just imagine a cube expanding, right? Each of its 3 sides, length, width, and height, gets a little bit longer. When you work out the math, it leads to this super simple relationship. The coefficient for volume expansion is just about 3 times the one for linear expansion. It's a fantastic shortcut to remember for exams.
But not everything plays by the rules. Water is the famous rebel here. As you cool water down, it shrinks, just like you'd expect. But then, between 4 degrees and 0 degrees Celsius, it does something totally bizarre. It starts to expand again. This means that water is at its absolute densest at 4 degrees Celsius, and this strange behavior has a huge impact on our planet. It's the reason lakes freeze from the top down, which insulates the water below and allows fish and other aquatic life to survive the winter. Pretty amazing, right? Okay, so we've seen that adding heat can raise temperature and make things expand. But now let's figure out how to actually measure that heat. And let's explore what happens when you add enough of it to completely change a substance's state. Like turning a solid into a liquid. You'll want to pay close attention to this one. Specific heat capacity is basically a measure of how much a substance resists changing its temperature. Think of it as thermal stubbornness. Water has a really high specific heat capacity. This is exactly why, on a hot day, the sand on a beach gets scorching hot, but the ocean water right next to it stays cool. The water needs way more energy to raise its temperature.
This graph is absolutely critical for understanding how states change. Look at what happens. As we heat ice, its temperature goes up until it hits 0 degrees Celsius. Then, something amazing happens. Even though we keep pumping in heat, the temperature stays totally flat until all the ice melts. Why? Because all that energy is being used to break the bonds holding the ice crystal together. The exact same thing happens again at 100 degrees when water boils. Those flat parts of the graph, that's where the magic of a phase change happens.
And that energy that's being used for the phase change, it has a special name, latent heat. The word latent literally means hidden, because it's energy that you're adding, but you don't see a temperature change. The latent heat of fusion is for melting, and the latent heat of vaporization is for boiling. This hidden heat is why a burn from steam at 100 degrees is so much more severe than a burn from water at 100 degrees. The steam is carrying a massive extra punch of energy.
Now for a concept that sounds like it's straight out of science fiction, the triple point. This is a very specific, unique combination of temperature and pressure where a substance can exist as a solid, a liquid, and a gas all at the exact same time, in perfect balance. And this isn't just a weird theory. The triple point of water is so incredibly precise and repeatable that scientists use it as the fundamental reference point for calibrating thermometers all over the world. So we've talked about what heat is, and we know how it can affect matter. But how does it actually get from one place to another? Well, it turns out there are 3 distinct ways that heat moves around.
And here they are, the 3 fundamental ways heat travels. You've got conduction, which is basically heat transfer by touch. Then there's convection, which is heat moving through the flow of fluids like air or water. And finally, you have radiation, which is heat transfer by waves, like the warmth you feel from the sun, which has to travel through the empty vacuum of space to reach us.
Let's look a little closer at conduction. The rate that heat flows is described by this formula. It shows us that heat flow, which we call H, moves much faster through materials that have a high thermal conductivity. That's the K in the equation. This explains perfectly why a good cooking pan has a copper bottom. Copper has a high K, so it's like a superhighway for heat. And it's also why you stir hot soup with a wooden spoon. Wood has a very low K, acting like a roadblock for heat and keeping your hand from getting burned.
Now for radiation, which is governed by the super powerful Stefan Boltzmann law. Now look closely at this formula. The really important thing to see is that the rate of energy radiation is proportional to the absolute temperature to the 4th power. That T to the 4th is a huge deal. It means if you double an object's absolute temperature, it radiates 16 times more energy. This is why things start to glow red hot and then white hot as their temperature absolutely skyrockets.
Okay, we have covered a ton of ground. So let's consolidate everything we've learned with a rapid-fire review of the key formulas from this chapter. Think of this as your quick reference sheet for any problem you'll need to solve.
All right, let's recap. We've got the ideal gas law, linking pressure, volume, and temp. The linear expansion formula for how much things grow. The specific heat formula for the energy needed to change temperature. The latent heat formula for the energy needed to change state. And the law of conduction, describing how fast heat flows through stuff. Mastering these equations is your ticket to acing this chapter. And to leave you with something big to think about, we learned that the hidden latent heat of vaporization is what makes steam burns so incredibly dangerous. Now think bigger, way bigger. That exact same principle, the release of enormous amounts of hidden energy when water vapor condenses back into liquid, is the very engine that powers colossal weather systems like hurricanes. The physics we talked about today doesn't just stay in the lab, it literally shapes our entire planet.